Picture this. You're floating in the infinite expanse of space, surrounded by a sea of darkness, so vast it defies comprehension. But this darkness isn't empty. It's alive, filled with an invisible tapestry of gas, dust, and energy, a cosmic dance that shapes the very fabric of the universe. This is the interstellar medium, the mysterious matter between stars, and it holds secrets that have fascinated astronomers for centuries. Tonight, as you drift into relaxation, let's journey together into this hidden realm, where stars are born, galaxies evolve, and the universe whispers its oldest stories. By the end of this video, you'll uncover how this seemingly empty space is anything but, and how it plays a crucial role in the grand story of the cosmos. So, where are you joining us from, and what time is it there? Let's dive into the wonders of the interstellar medium and explore the universe like never before. Now, let's take a closer look at what the interstellar medium actually is. Imagine it as the cosmic canvas on which the universe paints its most breathtaking masterpieces. The interstellar medium is the vast, invisible material that fills the space between stars. It's not just empty void, it's a dynamic mix of gas, dust, and high-energy particles called cosmic rays. This material is incredibly sparse, with densities far lower than anything we can create in a lab on Earth, but it's spread across such enormous distances that it adds up to a significant part of the universe's mass. The gas in the interstellar medium is mostly hydrogen, the simplest and most abundant element in the cosmos. Alongside it, you'll find helium and trace amounts of heavier elements like carbon, oxygen, and nitrogen. These elements are the building blocks of stars, planets, and even life itself. Then there's the dust, tiny particles made of carbon, silicon, and other materials. These grains are so small, they're measured in nanometers, but they play a huge role in shaping the light we see from distant stars and galaxies. Finally, cosmic rays zip through this mix at nearly the speed of light, carrying energy from explosive events like supernova. But why does this matter? The interstellar medium is the raw material for star formation. Without it, there would be no stars, no planets, and no galaxies. It's also a cosmic recycling system, where material from dying stars is returned to space, ready to form new stars and planets. This cycle has been going on for billions of years, shaping the universe as we know it. So, while it might seem like empty space, the interstellar medium is anything but. It's the lifeblood of the cosmos, quietly weaving the story of the universe. Now, let's turn our attention to one of the most fascinating roles of the interstellar medium, its part in the birth of stars. Picture this, scattered throughout the vast expanse of space. There are regions where the interstellar medium gathers into dense clouds, often referred to as molecular clouds. These clouds are like cosmic nurseries, where the raw materials for stars come together under the influence of gravity. The process begins when a portion of a molecular cloud becomes dense enough to start collapsing under its own gravity. This gravitational collapse is the first step in star formation. As the cloud contracts, it fragments into smaller clumps, each of which can eventually form a star. Within these clumps, The gas and dust continue to collapse, heating up as they compress. Over time, the core of the collapsing clump becomes so dense and hot that it forms what's known as a protostar, a baby star in the making. But it's not just gravity doing all the work. The interstellar medium's magnetic fields and turbulence also play crucial roles in shaping how these clumps form and evolve. Magnetic fields can slow down the collapse in some areas, while turbulence can stir up the gas, creating pockets of higher density. These interactions make the process of star formation incredibly complex and dynamic. As the protostar continues to grow, it gathers more material from its surroundings, pulling in gas and dust from the interstellar medium. This material spirals into the protostar, forming a disk around it. Over hundreds of thousands of years, the protostar's core becomes hot enough to ignite nuclear fusion, marking the birth of a new star. The leftover material in the disk can go on to form planets, moons, and other celestial bodies, completing the cycle of creation. This process isn't just a one-time event. It's happening all across the galaxy, in countless molecular clouds. Each star that forms is a testament to the interstellar medium's role as the ultimate cosmic recycler, turning the remnants of old stars into the building blocks of new ones. Without this intricate dance of gravity, gas, and dust, the universe as we know it simply wouldn't exist. Now, let's shift our focus to something equally mesmerizing, yet often overlooked: cosmic dust. These tiny particles, though small in size, play an enormous role in shaping the universe. Cosmic dust is made up of tiny grains, often no larger than a fraction of a millimeter, composed of elements like carbon, silicon, and iron. These grains are scattered throughout the interstellar medium, forming a kind of cosmic fog that fills the space between stars. But what makes cosmic dust so important? For one, it acts as a cosmic filter, absorbing and scattering light from stars and other celestial objects. This process, known as interstellar extinction, can make distant stars appear dimmer or redder than they actually are. Imagine looking at a streetlight through a foggy window. The light is still there, but it's altered by the particles in the air. Cosmic dust does something similar on a much grander scale, shaping how we see the universe. The distribution of cosmic dust isn't uniform. It tends to clump together in dense regions, often within molecular clouds, where it plays a key role in star formation. These dust grains provide surfaces for molecules to form, acting as tiny cosmic laboratories where complex chemical reactions take place. Over time, these molecules can become the building blocks for new stars and planets. Interestingly, cosmic dust also has a hand in creating some of the most stunning visual phenomena in space. When starlight interacts with these particles, it can scatter in all directions, creating beautiful reflection, nebulae. These glowing clouds of dust and gas often appear blue, as shorter wavelengths of light are scattered more effectively. On the other hand, when dust absorbs light and re-emits it at longer wavelengths, it can produce the warm, reddish glow of emission, nebulae. Despite its small size, cosmic dust has a profound impact on the universe. It shapes the light we see, influences the formation of stars and planets, and even plays a role in the chemistry of space. Without these tiny particles, the interstellar medium would be a very different place, and so would our understanding of the cosmos. As we continue to explore the universe, cosmic dust reminds us that even the smallest things can have a big impact. Now, let's turn our attention to the most abundant element in the universe, hydrogen. This simple yet essential element makes up about 75% of the visible matter in the cosmos and plays a starring role in the interstellar medium. Hydrogen exists in two primary forms here: atomic hydrogen and molecular hydrogen. Atomic hydrogen consists of single hydrogen atoms, while molecular hydrogen is made up of two hydrogen atoms bonded together. Both forms are crucial to the processes that shape the universe. Atomic hydrogen is found throughout the interstellar medium, often in regions of low density where temperatures are relatively high. These areas, known as the warm neutral medium, are filled with individual hydrogen atoms that emit faint radio waves. These emissions, detected by radio telescopes, help astronomers map the distribution of hydrogen across the galaxy. It's like listening to the whispers of the universe, revealing the hidden structure of space. Molecular hydrogen, on the other hand, thrives in colder, denser regions, particularly within molecular clouds. These clouds are the birthplaces of stars, and molecular hydrogen is their primary ingredient. When these clouds collapse under gravity, the hydrogen molecules break apart, allowing the gas to heat up and eventually ignite, forming new stars. Without molecular hydrogen, the process of star formation, as we know it, simply wouldn't happen. Hydrogen's importance doesn't stop there. It's also a key player in the chemistry of the interstellar medium. When hydrogen atoms combine with other elements, they form molecules like water, ammonia, and even simple organic compounds. These molecules, often found clinging to cosmic dust grains, are the building blocks for more complex chemistry, potentially setting the stage for the origins of life. The sheer abundance of hydrogen in the interstellar medium makes it a cornerstone of cosmic evolution. From fueling the birth of stars to enabling the chemistry that shapes planets and possibly life, hydrogen is truly the unsung hero of the universe. As we continue to explore the cosmos, understanding this element will remain central to unraveling the mysteries of how stars, galaxies, and even life itself come to be. Next, we'll explore how heavier elements, like helium and beyond, contribute to this cosmic tapestry. Now, let's shift our focus to another key player in the cosmic drama, helium. While hydrogen may dominate the interstellar medium, helium is the second most abundant element in the universe, making up about 24% of its visible matter. Together with hydrogen, these two elements form the foundation of the cosmos, but helium's story is just as fascinating and essential to the universe's evolution. Helium is primarily created in the hearts of stars through a process called nuclear fusion. When hydrogen atoms fuse together under immense pressure and temperature, they form helium, releasing vast amounts of energy in the process. This energy is what makes stars shine, but helium doesn't just stay locked away in stars forever. When massive stars reach the end of their lives and explode as supernova, they scatter helium and other elements into the interstellar medium, enriching it with the building blocks for future stars and planets. Beyond helium, the interstellar medium also contains trace amounts of heavier elements, often referred to as metals in astronomical terms. These elements, like carbon, oxygen, nitrogen, and iron, are forged in the intense environments of stars and supernova. While they make up only a tiny fraction of the interstellar medium, their presence is crucial. These heavier elements act as catalysts for complex chemical reactions, enabling the formation of molecules that are essential for the birth of stars and planets. For example, carbon and oxygen are key ingredients in the formation of carbon monoxide, a molecule that helps cool molecular clouds, allowing them to collapse and form new stars. Similarly, iron and silicon contribute to the formation of dust grains, which play a vital role in shielding young stars and planets from harmful radiation. Without these heavier elements, the universe as we know it would look very different. The presence of helium and heavier elements also influences the life cycle of stars. Helium, for instance, becomes the fuel for older stars once they've exhausted their hydrogen supply. In the later stages of a star's life, helium fusion produces even heavier elements like carbon and oxygen, which are then expelled into space when the star dies. This cycle of creation and dispersal ensures that the interstellar medium is constantly replenished with the materials needed for new stars, planets, and even life. As we look deeper into the cosmos, we see that helium and heavier elements are not just remnants of the past but active participants in the ongoing story of the universe. They shape the environments where stars are born, influence the chemistry of space, and ultimately contribute to the diversity of worlds we observe. Next, we'll explore how the temperature of the interstellar medium varies across different regions and what that means for the processes unfolding within it. Now, let's turn our attention to the temperature of the interstellar medium, a factor that plays a crucial role in shaping the cosmos. The interstellar medium is far from uniform when it comes to temperature. It ranges from the icy cold of molecular clouds to the searing heat of ionized gas, creating a dynamic and ever-changing environment. At one end of the spectrum, we find cold molecular clouds, where temperatures can drop to just a few degrees above absolute zero. These clouds are dense and filled with molecules like hydrogen and carbon monoxide, which thrive in such frigid conditions. The cold temperatures allow these molecules to clump together, forming the seeds of future stars and planets. Without these chilly regions, the process of star formation would be far less efficient, as the low temperatures help gravity overcome the pressure of gas, enabling collapse. On the other hand, the interstellar medium also contains regions of hot ionized gas, where temperatures can soar to hundreds of thousands or even millions of degrees. These areas are often found near massive stars or the remnants of supernova explosions. The intense heat ionizes the gas, stripping electrons from atoms and creating a plasma. This hot gas is less dense than the cold molecular clouds, but it plays a vital role in shaping the structure of the interstellar medium. It can carve out vast bubbles in space, pushing cooler gas aside and influencing where new stars can form. The temperature differences within the interstellar medium also affect how light travels through space. Cold molecular clouds are excellent at absorbing and scattering light, making them appear dark and opaque. In contrast, hot ionized gas emits light, often glowing brightly in visible or ultraviolet wavelengths. This interplay between absorption and emission creates the stunning visual contrasts we see in images of nebulae and star-forming regions. These temperature variations are not just a matter of curiosity. They have profound implications for the life cycle of stars and galaxies. Cold clouds provide the raw material for star formation, while hot gas helps regulate the process by heating and dispersing surrounding material. Together, they create a delicate balance that drives the evolution of the cosmos. As we continue our journey through the interstellar medium, we'll next explore the different types of interstellar clouds and how they serve as nurseries for stars and planets. Each type of cloud has its own unique characteristics, shaping the environments where new worlds are born. Now, shifting our gaze to the heart of star formation, we encounter interstellar clouds, vast, cosmic nurseries where stars and planets are born. These clouds come in different forms, each with its own unique characteristics and role in shaping the universe. Among them, molecular clouds and Roman II regions stand out as key players in the grand story of stellar creation. Molecular clouds are the coldest and densest regions of the interstellar medium. Here, temperatures plunge to just a few degrees above absolute zero, creating the perfect environment for molecules like hydrogen and carbon monoxide to thrive. These clouds are often referred to as stellar nurseries because they provide the raw material needed for star formation. Within their icy depths, gravity takes hold, pulling gas and dust together until they collapse into dense cores. Over time, these cores grow hotter and denser, eventually igniting nuclear fusion and giving birth to new stars. Without molecular clouds, the universe would lack the stars that light up galaxies and the planets that orbit them. In contrast, Roman II regions are hot, glowing clouds of ionized hydrogen gas. These regions form around massive, young stars that emit intense ultraviolet radiation. This radiation strips electrons from hydrogen atoms, creating a plasma that glows brightly in visible light. Roman II regions are often found near the edges of molecular clouds, where the energy from newly formed stars heats and ionizes the surrounding gas. While these regions are too hot for star formation to occur directly within them, they play a crucial role in shaping the interstellar medium. The powerful winds and radiation from massive stars can compress nearby molecular clouds, triggering the formation of even more stars. In this way, Roman II regions act as cosmic sculptors, carving out new pockets of star formation and influencing the structure of galaxies. Another fascinating type of interstellar cloud is the dark nebula. These dense clouds of dust and gas block the light from stars behind them, creating striking silhouettes against brighter backgrounds. While they may appear as voids in the night sky, dark nebulae are far from empty. They are rich in dust and molecules, making them potential sites for future star formation. Over time, the material within dark nebulae can collapse under its own gravity, forming new stars and planetary systems. Together, these interstellar clouds form a dynamic and interconnected network, each type contributing to the cycle of star and planet formation. Molecular clouds provide the raw materials, Roman 2 regions energize and shape the environment, and dark nebulae hide the seeds of future worlds. This intricate dance of gas, dust, and radiation ensures that the universe remains a place of constant creation and renewal. As we delve deeper into the mysteries of the interstellar medium, we'll next explore how supernova remnants enrich this cosmic tapestry, recycling matter and shaping the future of star formation. These explosive events leave behind a legacy that continues to influence the evolution of galaxies. Now, let's turn our attention to one of the most dramatic events in the cosmos, supernova explosions. These colossal bursts of energy mark the explosive end of a massive star's life, but they also serve as a cosmic recycling program, enriching the interstellar medium with the building blocks of future stars and planets. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity and then rebounds in a cataclysmic explosion. This explosion scatters the star's outer layers into space, seeding the surrounding interstellar medium with heavy elements like iron, gold, and uranium, elements forged in the star's core during its lifetime. The remnants of these explosions, known as supernova remnants, are vast, expanding clouds of gas and dust that continue to interact with the interstellar medium long after the initial blast. These remnants are not just chaotic debris, they are dynamic structures that play a vital role in shaping the galaxy. As the shock waves from the explosion travel outward, they compress and heat the surrounding gas, triggering the formation of new stars and even entire star clusters. In this way, supernova remnants act as cosmic catalysts, sparking new cycles of stellar birth and evolution. But the influence of supernova remnants goes beyond star formation. The heavy elements they release into the interstellar medium are essential for the creation of planets, moons, and even life itself. Elements like carbon, oxygen, and nitrogen, crucial for organic molecules, are dispersed throughout the galaxy by these explosions. Without supernova, the universe would lack the diversity of elements needed to form complex structures, from rocky planets to the molecules that make up living organisms. Supernova remnants also leave behind fascinating structures, such as pulsars and neutron stars, which continue to interact with their surroundings. These dense, rapidly spinning objects emit powerful radiation and magnetic fields, further influencing the interstellar medium. Over time, the material from supernova remnants mixes with the surrounding gas and dust, becoming part of the raw material for future generations of stars and planets. As we look ahead, the next chapter of our journey takes us into the realm of cosmic rays, high-energy particles that race through the interstellar medium, shaping its properties and revealing the dynamic nature of our galaxy. These particles, born in the aftermath of supernova, carry with them the echoes of these explosive events, connecting the past and future of the cosmos. Now, let's venture into the mysterious world of cosmic rays, high-energy particles that zip through the vast expanse of the interstellar medium, carrying secrets of the universe's most powerful events. These particles, which include protons, electrons, and atomic nuclei, are accelerated to nearly the speed of light, making them some of the most energetic phenomena in the cosmos. But where do they come from, and how do they shape the interstellar medium? Cosmic rays are born in the aftermath of some of the universe's most violent events, such as supernova explosions. When a massive star explodes, the shock waves from the blast accelerate particles to incredible speeds, flinging them into space. These particles then travel across the galaxy, weaving through the interstellar medium like cosmic messengers. Along their journey, they interact with the gas and dust, leaving behind a trail of ionized atoms and molecules. This process of ionization plays a crucial role in shaping the properties of the interstellar medium, influencing everything from star formation to the structure of galaxies. But cosmic rays don't just ionize gas, they also help us understand the universe in profound ways. By studying these particles, scientists can trace their origins back to the explosive events that created them, offering insights into the life cycles of stars and the dynamics of the interstellar medium. For example, when cosmic rays collide with atoms in the interstellar medium, they produce gamma rays and other secondary particles, which astronomers can detect and analyze. These observations provide a window into the high-energy processes that drive the evolution of galaxies. Interestingly, cosmic rays also play a role in the chemistry of the interstellar medium. When they collide with molecules, they can trigger reactions that lead to the formation of complex organic compounds, some of which are the building blocks of life. This means that cosmic rays not only shape the physical structure of the interstellar medium, but also contribute to the chemical diversity that makes life possible. As we continue to explore the interstellar medium, cosmic rays remind us of the interconnectedness of the universe. They link the explosive deaths of stars to the birth of new worlds, and they carry with them the echoes of cosmic events that occurred millions or even billions of years ago. Their journey through the interstellar medium is a testament to the dynamic and ever-changing nature of our galaxy. Looking ahead, our exploration takes us to the invisible forces that shape the interstellar medium, magnetic fields. These unseen threads weave through the fabric of space, influencing the movement of gas and dust, and playing a vital role in the formation of stars and planets. Now, let's turn our attention to the invisible yet powerful forces that silently shape the interstellar medium, magnetic fields. These unseen threads stretch across the vastness of space, weaving through clouds of gas and dust, and playing a crucial role in the cosmic dance of star formation and galactic evolution. Though we can't see them directly, their influence is everywhere, guiding the movement of matter and sculpting the structure of the universe. Magnetic fields in the interstellar medium are generated by the motion of charged particles, such as electrons and ions, as they move through space. These fields are incredibly weak compared to those we encounter on Earth, but over the immense distances of space, their effects add up. They act like cosmic highways, channeling the flow of gas and dust, and even influencing the paths of cosmic rays. Without these magnetic fields, the interstellar medium would be far more chaotic, and the processes that lead to star formation would be drastically different. One of the most fascinating roles of interstellar magnetic fields is their ability to shape the structure of molecular clouds, the birthplaces of stars. As gravity pulls gas and dust together to form these clouds, magnetic fields resist the collapse, creating a delicate balance. This resistance slows down the process, allowing the cloud to fragment into smaller clumps that eventually become stars. In this way, magnetic fields act as cosmic sculptors, ensuring that stars form in an orderly and controlled manner. But magnetic fields don't just influence star formation, they also affect the way gas and dust move within the interstellar medium. For example, they can align dust grains, causing them to emit polarized light. This polarization provides astronomers with valuable clues about the strength and direction of magnetic fields in different regions of space. By studying this light, scientists can map out the invisible magnetic landscape, revealing how these fields shape the interstellar medium on both small and large scales. Another remarkable aspect of interstellar magnetic fields is their role in regulating the flow of energy. When cosmic rays or stellar winds interact with the interstellar medium, magnetic fields can channel and redirect this energy, preventing it from dissipating too quickly. This process helps maintain the delicate balance of temperatures and pressures within the medium, ensuring that conditions remain suitable for star formation and other cosmic processes. As we continue to explore the interstellar medium, magnetic fields remind us that the universe is governed by forces we cannot always see. They are the silent architects of the cosmos, shaping the gas and dust that give rise to stars, planets, and even life itself. Their presence is a testament to the intricate and interconnected nature of the universe, where even the most invisible forces play a vital role in the grand tapestry of creation. Next, we'll delve into the fascinating chemistry of the interstellar medium, where molecules form in the cold, dark depths of space, setting the stage for the emergence of complex compounds and the potential for life. Now, let's journey into the cold, dark depths of space, where something extraordinary is happening in chemistry. Yes, even in the vast emptiness of the interstellar medium, molecules are forming, creating the building blocks for everything from water to complex organic compounds. This interstellar chemistry is a quiet but essential process, setting the stage for the emergence of life itself. In the frigid environment of space, where temperatures can drop to just a few degrees above absolute zero, atoms and molecules move slowly, allowing them to collide and bond in ways that would be impossible in warmer, more chaotic settings. These collisions give rise to simple molecules like hydrogen, carbon monoxide, and even water. But it doesn't stop there. Over time, these simple molecules can combine to form more complex ones, including organic compounds like formaldehyde and methanol. One of the most fascinating aspects of interstellar chemistry is how these molecules form in the first place. In the absence of solid surfaces, most of these reactions happen on the surfaces of tiny dust grains. These grains act as cosmic laboratories, providing a place for atoms to meet and bond. For example, hydrogen atoms can stick to a dust grain and combine with oxygen atoms to form water molecules. Once formed, these molecules can be released back into space, where they become part of the interstellar medium. But the story doesn't end with simple molecules. In the dense cores of molecular clouds, where conditions are just right, even more complex chemistry takes place. Here, Ultraviolet light from nearby stars or cosmic rays can trigger reactions that produce amino acids and other prebiotic molecules, the very ingredients needed for life. These molecules are then carried by stellar winds or incorporated into new stars and planets, potentially seeding the universe with the raw materials for life. Interstellar chemistry also plays a crucial role in the life cycle of stars and galaxies. As stars form and die, they release heavy elements like carbon, nitrogen, and oxygen into the interstellar medium. These elements become part of the chemical soup, enriching the medium and allowing for the formation of even more complex molecules. Over billions of years, this cycle of creation and destruction shapes the chemical makeup of the universe, influencing everything from the formation of planets to the potential for life. What's truly remarkable is that we can observe these chemical processes happening in real time. Using powerful telescopes, astronomers have detected the signatures of hundreds of different molecules in space, from simple ones like water to more complex organic compounds. These observations not only reveal the richness of interstellar chemistry, but also provide clues about the origins of life on Earth and the possibility of life elsewhere in the universe. As we continue to explore the interstellar medium, the chemistry of space reminds us that even in the coldest, darkest corners of the cosmos, the building blocks of life are being forged. It's a testament to the incredible complexity and interconnectedness of the universe, where even the smallest molecules play a part in the grand story of creation. Next, we'll explore how the interstellar medium contributes to the life cycle of galaxies, shaping their evolution and influencing the birth and death of stars. Now, let's shift our gaze to the bigger picture and explore how the interstellar medium shapes the very fabric of galaxies. This vast, dynamic reservoir of gas and dust doesn't just exist in isolation. It's a driving force behind the life cycle of galaxies, influencing everything from the birth of stars to the sweeping currents of galactic winds. At the heart of galactic evolution lies star formation, and the interstellar medium is its primary fuel source. When dense regions within the medium collapse under gravity, they give birth to new stars. These stars, in turn, illuminate their surroundings, heat the gas, and even trigger further star formation through shock waves from their powerful stellar winds. Over time, this cycle of star birth and death transforms the interstellar medium, enriching it with heavier elements forged in the cores of stars. But the interstellar medium's role doesn't end with star formation. As stars age and die, they release their material back into space through processes like supernova explosions and stellar winds. This recycled matter becomes part of the interstellar medium once again, creating a continuous loop of creation and destruction. This cycle not only replenishes the medium, but also changes its chemical composition, making it richer in elements like carbon, oxygen, and nitrogen, elements essential for the formation of planets and, potentially, life. Galactic winds, driven by the energy of supernova and the radiation from massive stars, also play a crucial role. These winds can sweep through the interstellar medium, pushing gas and dust out of a galaxy's central regions and into its outer reaches. In some cases, they can even eject material entirely, shaping the galaxy's structure and influencing its future evolution. These outflows can regulate star formation by removing the raw materials needed to create new stars, effectively putting a brake on the process. On a larger scale, the interstellar medium connects galaxies to the cosmic web, the vast network of gas and dark matter that spans the universe. Through this connection, galaxies can exchange material, grow, and evolve over billions of years. The interstellar medium acts as a bridge, linking the smallest processes like the formation of molecules to the grandest structures in the cosmos. What's truly fascinating is how this intricate dance of matter and energy shapes the diversity of galaxies we see today. From spiral galaxies with their swirling arms of gas and dust, to elliptical galaxies where star formation has largely ceased, the interstellar medium plays a central role in determining a galaxy's fate. It's a reminder that even the smallest particles in space are part of a much larger story, one that spans the entire universe. As we continue to unravel the mysteries of the interstellar medium, we gain a deeper understanding of how galaxies evolve, grow, and change over time. It's a story of transformation, where the tiniest grains of dust and the faintest wisps of gas contribute to the grand tapestry of cosmic history. Next, we'll dive into how the interstellar medium interacts with light, creating some of the most stunning visual phenomena in the universe. Now, let's turn our attention to the interplay between the interstellar medium and light, a relationship that paints the cosmos with some of its most breathtaking sights. The interstellar medium doesn't just sit quietly in the darkness, it actively interacts with light, shaping how we see the universe and revealing its hidden secrets. One of the most fascinating ways the interstellar medium interacts with light is through absorption. As light from distant stars and galaxies travels through space, it passes through clouds of gas and dust in the interstellar medium. These clouds can absorb certain wavelengths of light, leaving behind dark lines in the spectrum known as absorption lines. These lines act like cosmic fingerprints, telling astronomers about the composition, temperature, and density of the gas and dust that the light has passed through. By studying these absorption lines, scientists can piece together the story of what lies between the stars. But the interstellar medium doesn't just absorb light, it also emits it. Emission nebulae are glowing clouds of gas that light up when they're energized by nearby stars. These stars emit intense ultraviolet radiation, which ionizes the gas in the nebula, stripping electrons from atoms. When these electrons recombine with the atoms, they release energy in the form of light, creating the vibrant colors we see in nebulae like the Orion Nebula. The specific colors depend on the types of gas present. Hydrogen, for example, glows red, while oxygen emits a bluish-green light. These glowing clouds are not just beautiful, they are also crucial laboratories for studying the processes that shape the universe. Another stunning phenomenon created by the interstellar medium is reflection nebulae. Unlike emission nebulae, which glow on their own, reflection nebulae shine by scattering the light of nearby stars. Dust particles in these nebulae reflect starlight, often giving them a bluish hue because shorter wavelengths of light, like blue, scatter more easily than longer wavelengths. The result is a cosmic mirror, capturing and redirecting the light of stars in a way that creates ethereal, glowing landscapes. The interstellar medium also plays a role in creating some of the most dramatic visual contrasts in space. Dark nebulae, dense clouds of gas and dust, block the light from stars and galaxies behind them, creating stark silhouettes against brighter backgrounds. These dark patches, like the famous Horsehead Nebula, remind us that the interstellar medium isn't just a passive backdrop, it's an active participant in the cosmic drama, shaping the light we see and the stories we tell about the universe. Through these interactions with light, the interstellar medium reveals its dynamic nature. It absorbs, emits, and scatters light, creating a kaleidoscope of colors and patterns that captivate our imagination. These phenomena aren't just beautiful, they are also essential tools for astronomers, helping us understand the composition, structure, and evolution of the universe. Next, we'll explore how these processes connect to the life cycle of stars, showing how the interstellar medium is not just a stage for cosmic events, but a key player in the story of the universe. Now, let's venture into the shadowy realms of the cosmos, where the interstellar medium takes on a more mysterious form. Dark nebulae, these dense clouds of gas and dust, are the hidden corners of space, often invisible to the naked eye, yet they play a crucial role in shaping the visual tapestry of the universe. Unlike their glowing counterparts, dark nebulae don't emit or reflect light. Instead, they absorb and block it, creating dramatic contrasts that reveal their presence in the most striking ways. Dark nebulae are composed primarily of cold molecular gas and tiny dust particles, which are so thick and concentrated that they prevent light from passing through. Imagine a dense fog on a moonless night, obscuring everything in its path. In the same way, these cosmic clouds obscure the light from stars and galaxies behind them, casting dark silhouettes against the brighter backgrounds of space. One of the most famous examples is the Horsehead Nebula, a dark cloud that stands out vividly against the glowing gas of the Orion Nebula. Its distinctive shape, resembling a horse's head, has made it an iconic image in astronomy. But dark nebulae are more than just cosmic shadows. They are also the birthplaces of stars. Within these cold, dense clouds, gravity begins to pull the gas and dust together, forming clumps that eventually collapse under their own weight. As these clumps grow denser and hotter, they ignite the process of star formation. In this way, dark nebulae are like cosmic nurseries, hidden from view but teeming with potential. They remind us that even in the darkest corners of space, new beginnings are taking shape. The composition of dark nebulae is also fascinating. While they are mostly made up of hydrogen molecules, they also contain trace amounts of other elements, as well as complex molecules like carbon monoxide and even organic compounds. These molecules are the building blocks of more complex chemistry, hinting at the possibility of life-forming processes occurring within these seemingly barren clouds. By studying the composition of dark nebulae, scientists can gain insights into the chemical evolution of the universe and the origins of the materials that make up stars, planets, and even life itself. What makes dark nebulae truly captivating is their ability to create stark, almost artistic contrasts in the night sky. Against the backdrop of glowing nebulae, and star-filled regions, they stand out as dark, intricate shapes, like ink blots on a canvas of light. These silhouettes not only add depth and drama to our view of the cosmos, but also serve as a reminder of the interstellar medium's dynamic nature. It's not just a passive observer, it's an active participant, shaping the light and the stories we see in the universe. As we continue our journey through the interstellar medium, we'll next explore how these dark nebulae connect to the broader life cycle of stars, revealing how even the darkest corners of space are part of the grand cosmic dance. Now, let's turn our gaze to a different kind of cosmic wonder, reflection nebulae. Unlike the dark, light-absorbing clouds we've just explored, reflection nebulae are like cosmic mirrors, scattering and reflecting the light of nearby stars. These ethereal clouds are made up of fine dust particles that don't emit their own light, but instead catch and scatter the light from stars, creating a soft, glowing effect that can be breathtaking to behold. Imagine a beam of sunlight filtering through a dusty room, illuminating the tiny particles in the air. In much the same way, reflection nebulae capture and scatter starlight, transforming it into a diffuse glow that paints the surrounding space with delicate hues of blue and white. This scattering effect, known as Rayleigh scattering, is the same phenomenon that makes our sky appear blue during the day. In the case of reflection nebulae, the fine dust particles preferentially scatter shorter wavelengths of light, giving these nebulae their characteristic bluish tint. One of the most famous examples of a reflection nebula is the Witch Head Nebula, located near the bright star Rigel in the constellation Orion. Its wispy, ghostly appearance seems to stretch across the sky like a spectral hand, illuminated by the light of Rigel. Another stunning example is the Pleiades star cluster, often referred to as the Seven Sisters. The faint, bluish glow surrounding these stars is caused by a reflection nebula, adding an extra layer of beauty to this already dazzling cluster. Reflection nebulae are not just visually stunning, they also play an important role in the interstellar medium. By scattering starlight, they help to illuminate the surrounding gas and dust, revealing structures and features that might otherwise remain hidden. This scattered light can also heat the surrounding dust, influencing the temperature and dynamics of the interstellar medium. In this way, reflection nebulae are more than just passive reflectors. They actively shape their environment, contributing to the complex interplay of light and matter in space. What makes reflection nebulae truly captivating is their ability to transform the light of stars into something entirely new. They take the raw brilliance of starlight and soften it, diffusing it into a gentle glow that seems to breathe life into the darkness of space. These cosmic mirrors remind us that even in the vast emptiness of the universe, light finds a way to create beauty, weaving intricate patterns that inspire awe and wonder. As we continue our journey through the interstellar medium, we'll next explore the vibrant and glowing world of emission nebulae, where the interplay of light and gas creates some of the most spectacular sights in the cosmos. Now, let's step into the vibrant world of emission nebulae, where the cosmos comes alive with glowing clouds of ionized gas. Unlike reflection nebulae, which scatter starlight, emission nebulae are powered by the intense energy of nearby stars, causing them to emit their own light. These dazzling regions of space are often filled with hydrogen gas, which becomes ionized when exposed to the ultraviolet radiation from hot, young stars. This ionization process strips electrons from hydrogen atoms, and when those electrons recombine with protons, they release energy in the form of light, creating the stunning glow that defines emission nebulae. One of the most iconic examples of an emission nebula is the Orion Nebula, a sprawling cloud of gas and dust located in the constellation Orion. This nebula is a stellar nursery where new stars are born from the dense pockets of gas. The intense radiation from these young stars ionizes the surrounding hydrogen, causing the nebula to glow with a rich, reddish hue. This color is characteristic of hydrogen emission, often referred to as H-alpha light, and it's a hallmark of many emission nebulae. Another breathtaking example is the Lagoon Nebula, a vast cloud of gas and dust located in the constellation Sagittarius. Here, the interplay of light and gas creates a dynamic landscape of glowing filaments and dark, dusty lanes. The Lagoon Nebula is home to numerous young stars, whose radiation ionizes the surrounding gas, producing a vivid display of colors ranging from deep reds to soft pinks. These regions are not just beautiful, they're also crucial to the life cycle of stars, as they provide the raw material for new stellar births. The process of ionization doesn't just create light, it also shapes the structure of the nebula itself. As the ionized gas expands and interacts with the surrounding material, it can carve out intricate patterns and cavities, creating the dramatic shapes we see in images of emission nebulae. These structures are often illuminated by the light of the very stars that ionize the gas, creating a feedback loop where stars and nebulae influence each other's evolution. Emission nebulae are more than just cosmic light shows. They're also windows into the processes that drive star formation and galactic evolution. By studying these glowing clouds, astronomers can learn about the conditions that give rise to new stars and the ways in which stars and nebulae interact over time. These nebulae remind us that the universe is a dynamic, ever-changing place, where light and matter are constantly reshaping the cosmos. As we move forward, we'll explore how these glowing clouds of ionized gas connect to the broader story of the interstellar medium, revealing the intricate web of interactions that shape the universe we see today. Now, let's take a closer look at how the interstellar medium plays a vital role in the life cycle of stars, a process that spans billions of years and shapes the very fabric of the universe. The interstellar medium is not just a passive backdrop, it's the raw material from which stars are born and the repository to which they return at the end of their lives. This continuous cycle of creation and destruction is one of the most fundamental processes in the cosmos. The journey begins in the cold, dense regions of the interstellar medium, known as molecular clouds. These clouds, rich in hydrogen and dust, are the birthplaces of stars. Under the influence of gravity, pockets of gas within these clouds begin to collapse, growing denser and hotter until nuclear fusion ignites at their cores. This marks the birth of a star, and the surrounding interstellar medium provides the fuel for its growth. Over time, the star's radiation and stellar winds push back against the remaining gas, carving out cavities and shaping the surrounding nebula. But the story doesn't end there. As stars age, they continue to interact with the interstellar medium in profound ways. Massive stars, for example, burn through their fuel quickly and end their lives in spectacular supernova explosions. These cataclysmic events blast the star's outer layers back into space, enriching the interstellar medium with heavy elements like carbon, oxygen, and iron. These elements, forged in the hearts of stars, become the building blocks for new stars, planets, and even life itself. Smaller stars, like our Sun, have a gentler but no less important role in this cycle. As they exhaust their fuel, they shed their outer layers, creating beautiful planetary nebulae. These glowing shells of gas and dust gradually disperse into the interstellar medium, replenishing it with the materials needed for future star formation. Even the remnants of dead stars, such as white dwarfs, neutron stars, and black holes, continue to influence the interstellar medium through their gravitational pull and energy emissions. This ongoing exchange of matter between stars and the interstellar medium is what keeps the universe dynamic and ever-changing. It's a reminder that the cosmos is not static. It's a living, breathing system where matter is constantly recycled and repurposed. From the birth of stars in dense molecular clouds to the explosive deaths of massive stars, the interstellar medium is both the cradle and the graveyard of stellar life. As we continue our journey, we'll explore how these processes extend beyond individual stars, shaping the evolution of entire galaxies and the large-scale structure of the universe. The interstellar medium is not just a collection of gas and dust. It's the thread that weaves together the story of the cosmos, connecting the past, present, and future of the universe. Now, let's turn our attention to another fascinating aspect of the interstellar medium: interstellar winds. These are not the gentle breezes we experience on Earth, but powerful streams of gas and dust that flow through the vast expanses of space. Interstellar winds play a crucial role in shaping the distribution of matter in galaxies, influencing everything from star formation to the structure of the cosmos itself. Interstellar winds are driven by a variety of forces. One of the primary sources is the intense radiation and stellar winds emitted by massive stars. As these stars burn brightly, they release streams of charged particles and energy that push against the surrounding gas and dust. Over time, this creates a kind of cosmic wind that sweeps through the interstellar medium, carving out bubbles and cavities in the gas clouds. These winds can even trigger the collapse of nearby gas clouds, setting the stage for new stars to form. Supernova explosions are another major contributor to interstellar winds. When a massive star reaches the end of its life and explodes, it sends shockwaves rippling through the interstellar medium. These shockwaves can accelerate particles to incredible speeds, creating high-velocity winds that spread heavy elements far and wide. This process not only redistributes matter, but also enriches the interstellar medium with the building blocks needed for future generations of stars and planets. But interstellar winds aren't just the result of stellar activity. They can also be influenced by the rotation of galaxies and the gravitational pull of massive objects like black holes. As galaxies spin, they create a kind of galactic wind that flows outward from the center, carrying gas and dust with it. This movement helps to regulate the density of the interstellar medium, ensuring that matter is distributed more evenly throughout the galaxy. The impact of interstellar winds is profound. They help to regulate the rate of star formation by dispersing gas clouds or compressing them to trigger new star birth. They also play a key role in shaping the large-scale structure of galaxies, creating intricate patterns of gas and dust that can be seen in stunning astronomical images. Without these winds, the interstellar medium would be far more static, and the dynamic processes that drive the evolution of galaxies would grind to a halt. As we continue to explore the mysteries of the interstellar medium, interstellar winds remind us of the interconnectedness of the cosmos. They are a testament to the constant motion and change that define the universe, from the smallest particles of dust to the grandest structures in space. Next, we'll delve into how these winds, along with other forces, contribute to the search for extraterrestrial life and the potential for life beyond our own planet. Now, let's shift our gaze to one of the most intriguing questions in science. Could the interstellar medium hold the key to finding life beyond Earth? This vast expanse of gas and dust isn't just a backdrop for stars and galaxies, it's a cosmic laboratory where the building blocks of life might be hiding. The interstellar medium is rich with complex molecules, some of which are essential for life as we know it. Water, for example, has been detected in the form of ice, clinging to dust grains in cold molecular clouds. Even more fascinating, organic molecules like amino acids, the very components of proteins, have been found floating in space. These discoveries suggest that the raw ingredients for life might be scattered throughout the galaxy, waiting for the right conditions to spark something extraordinary. But how do these molecules form in the harsh environment of space? It turns out that cosmic dust plays a crucial role. Tiny grains of dust act as tiny factories, providing surfaces where atoms and molecules can come together and react. Over time, these reactions can create more complex compounds, some of which might be precursors to life. Even the radiation from stars, which might seem destructive, can actually help drive these chemical processes, adding energy to the mix and enabling new reactions to occur. The interstellar medium also acts as a kind of cosmic delivery system. When stars form, they pull in material from their surroundings, including these prebiotic molecules. Later, when stars die and explode as supernova, they scatter these molecules back into space, seeding the interstellar medium with the potential for life once again. This cycle of creation and destruction ensures that the building blocks of life are continually recycled and distributed across the galaxy. But the interstellar medium doesn't just provide the ingredients for life. It might also influence where and how life could arise. For example, the density and temperature of interstellar clouds can determine whether planets form around stars and what kinds of atmospheres those planets might have. A planet forming in a region rich in organic molecules might have a better chance of developing life than one in a more barren part of space. As we search for signs of extraterrestrial life, the interstellar medium offers a treasure trove of clues. By studying the chemistry of distant gas clouds, we can learn more about the conditions that might support life elsewhere in the universe. Missions like the James Webb Space Telescope are already peering into these clouds, analyzing their composition and searching for signs of habitable environments. The interstellar medium reminds us that life, if it exists beyond Earth, is deeply connected to the cosmos. It's not just about finding planets with the right conditions. It's about understanding how the universe itself creates and distributes the ingredients for life. As we continue to explore, the interstellar medium may hold the answers to one of humanity's oldest questions. Are we alone in the universe? Next, we'll take a closer look at how the interstellar medium varies in other galaxies and what that tells us about the diversity of the cosmos. Now, let's journey beyond our own galaxy and explore how the interstellar medium exists in other corners of the universe. While we often think of the Milky Way as the center of our cosmic experience, the interstellar medium is a universal phenomenon present in galaxies near and far. What's fascinating is that, despite the vast distances between galaxies, the interstellar medium shares many common traits across the cosmos, yet each galaxy adds its own unique twist to the story. In our Milky Way, the interstellar medium is a dynamic mix of gas, dust, and cosmic rays, with regions of cold molecular clouds and hot ionized gas. But when we look at other galaxies, we see similar ingredients, though often arranged in different ways. For example, spiral galaxies like the Milky Way tend to have a more structured interstellar medium, with dense clouds concentrated along their spiral arms. These regions are often bustling with star formation, much like the nurseries we see in our own galaxy. Elliptical galaxies, on the other hand, tell a different tale. These galaxies are typically older and have less gas and dust compared to spirals. Their interstellar medium is often dominated by hot, ionized gas, with fewer cold clouds where stars can form. This difference in composition means that elliptical galaxies are less active in terms of star formation, giving them a quieter, more settled appearance. Then there are irregular galaxies, which defy the neat classifications of spirals and ellipticals. These galaxies are often chaotic, with a jumbled mix of gas, dust, and stars. Their interstellar medium can be incredibly rich in raw materials, leading to bursts of intense star formation. In some cases, irregular galaxies are the result of collisions or interactions with other galaxies, which stir up their interstellar medium and trigger new waves of stellar birth. One of the most striking similarities across galaxies is the role of supernova. Just as in the Milky Way, exploding stars in other galaxies enrich their interstellar medium with heavy elements, seeding the next generation of stars and planets. This process of recycling matter is universal, ensuring that the building blocks of life are spread far and wide, but there are also intriguing differences. For instance, the amount of dust in a galaxy's interstellar medium can vary dramatically. Some galaxies, particularly those in the early universe, have very little dust, making their interstellar medium almost transparent. Others, like starburst galaxies, are so rich in dust that they glow brightly in infrared light as the dust absorbs and emits the energy from young, hot stars. Studying the interstellar medium in other galaxies also gives us a glimpse into the past. By observing distant galaxies, we can see how the interstellar medium has evolved over billions of years. In the early universe, galaxies were smaller, and their interstellar medium was less enriched with heavy elements. Over time, as stars lived and died, they transformed the interstellar medium, making it richer and more complex. This universal perspective reminds us that the Milky Way is just one piece of a much larger puzzle. The interstellar medium connects galaxies across the cosmos, shaping their evolution and influencing the birth of stars and planets. By comparing our galaxy to others, we gain a deeper understanding of the processes that drive the universe, and perhaps even the origins of life itself. Next, we'll explore how the interstellar medium serves as a window into the early universe, revealing clues about the dawn of cosmic time. Now, let's turn our gaze back in time, using the interstellar medium as a cosmic time machine. By studying this vast expanse of gas and dust, we can uncover secrets about the early universe and how matter has evolved over billions of years. The interstellar medium isn't just a backdrop for stars and galaxies. It's a living record of the universe's history, preserving clues about the conditions that shaped everything we see today. When we look at distant galaxies, we're essentially peering into the past. Light from these galaxies takes millions, or even billions, of years to reach us, meaning we see them as they were long ago. By analyzing the interstellar medium in these ancient galaxies, we can piece together how the universe looked in its infancy. For example, in the early universe, galaxies were smaller, and their interstellar medium was much simpler, composed mostly of hydrogen and helium, the elements forged in the Big Bang. Over time, as stars formed, lived, and died, they enriched the interstellar medium with heavier elements like carbon, oxygen, and iron, creating the complex chemistry we see today. One of the most fascinating discoveries is how the interstellar medium has changed over cosmic time. In the early universe, galaxies were more chaotic, with intense bursts of star formation and frequent collisions. These events stirred up the interstellar medium, creating turbulent environments where stars could form rapidly. Over billions of years, as galaxies matured, their interstellar medium became more stable, with cooler, denser clouds that allowed for slower, more sustained star formation. This shift in the interstellar medium's behavior has shaped the evolution of galaxies, influencing everything from their structure to their ability to form planets. Another key insight comes from studying the abundance of heavy elements, or metals, in the interstellar medium. In the early universe, these elements were rare, but as generations of stars exploded as supernova, they scattered these metals across space, enriching the interstellar medium. This process, known as chemical evolution, has transformed the universe from a simple, hydrogen-dominated place to one filled with complex molecules and the building blocks of life. By measuring the metal content in the interstellar medium of ancient galaxies, astronomers can trace the history of star formation and understand how the universe became the rich, diverse place it is today. The interstellar medium also holds clues about the universe's expansion and the formation of large-scale structures. In the early universe, tiny fluctuations in the density of matter, led to the formation of the first galaxies and the cosmic web, the vast network of gas and dark matter that connects galaxies across the cosmos. The interstellar medium within these structures has evolved alongside them, reflecting the growth and movement of galaxies over time. By studying these patterns, scientists can test theories about the universe's origins and its ultimate fate. In many ways, the interstellar medium is like a cosmic archive, preserving the story of the universe's evolution. From the first stars to the galaxies we see today, it has played a central role in shaping the cosmos. By unlocking its secrets, we gain not only a deeper understanding of the past, but also a clearer picture of how the universe will continue to change in the future. Next, we'll explore the tools and techniques astronomers use to study this remarkable medium, revealing how we uncover its hidden stories. Now, let's shift our focus to the tools and techniques that allow us to uncover the secrets of the interstellar medium. To study this vast and complex expanse, astronomers rely on a variety of advanced instruments and methods, each offering a unique window into the cosmos. One of the most powerful tools at their disposal is the telescope. From ground-based observatories to space telescopes like the Hubble and James Webb, these instruments capture light from distant stars, galaxies, and the interstellar medium itself. By observing the light that passes through or is emitted by the interstellar medium, astronomers can analyze its composition, density, and temperature. Another critical technique is spectroscopy, which involves breaking down light into its component colors, or wavelengths. When light from a star passes through the interstellar medium, certain wavelengths are absorbed by the gas and dust, creating dark lines in the spectrum. These absorption lines act like fingerprints, revealing the presence of specific elements and molecules in the interstellar medium. For example, hydrogen, the most abundant element, leaves a distinct signature that astronomers can easily identify. Spectroscopy also helps scientists measure the velocity of gas clouds, providing insights into how the interstellar medium moves and interacts with stars and galaxies. Radio astronomy plays an equally important role in studying the interstellar medium. Unlike visible light, radio waves can penetrate dense clouds of dust that would otherwise block our view. Radio telescopes detect emissions from molecules like carbon monoxide and water, which are common in the interstellar medium. These observations allow astronomers to map the distribution of gas and dust in great detail, revealing the structure of molecular clouds where stars are born. Additionally, radio astronomy helps us study phenomena like supernova remnants and the magnetic fields that thread through the interstellar medium, offering a deeper understanding of its dynamic nature. Infrared observations are another key tool, especially for studying cosmic dust. Dust grains in the interstellar medium absorb visible light and re-emit it as infrared radiation. Space telescopes like the Spitzer and the James Webb are equipped with infrared detectors that can peer through dusty regions, uncovering hidden star-forming areas and providing a clearer picture of the interstellar medium's role in galaxy evolution. By combining data from different wavelengths, visible, radio, and infrared, astronomers can piece together a comprehensive view of this complex medium. One of the most exciting developments in recent years is the use of interferometry, a technique that combines signals from multiple telescopes to create a virtual telescope with unprecedented resolution. This method has allowed astronomers to study the interstellar medium in extraordinary detail, revealing structures and processes that were previously invisible. For example, interferometry has been used to observe the intricate motions of gas within star-forming regions, shedding light on how stars and planetary systems take shape. As technology continues to advance, so too does our ability to explore the interstellar medium. From cutting-edge telescopes to innovative data analysis techniques, these tools are helping us unlock the mysteries of the universe's hidden matter. Next, we'll delve into the connection between the interstellar medium and the cosmic web, exploring how this vast network of gas and dark matter shapes the universe on the largest scales. Now, let's take a step back and look at the bigger picture. The interstellar medium isn't just a collection of gas and dust scattered randomly across the galaxy. It's part of something much larger, a vast cosmic tapestry known as the cosmic web. This intricate network of matter stretches across the universe, connecting galaxies, clusters, and even the voids between them. But how does the interstellar medium fit into this grand structure? Let's find out. The cosmic web is made up of filaments, nodes, and voids, forming a kind of skeleton that defines the large-scale structure of the universe. These filaments are long, thread-like structures composed of gas, dark matter, and the interstellar medium itself. They act as highways, channeling matter from one part of the universe to another. At the intersections of these filaments, you'll find galaxy clusters, some of the most massive structures in the cosmos. Meanwhile, the voids are vast, nearly empty regions where matter is sparse. Together, these elements create a web-like pattern that astronomers have been mapping for decades. So, where does the interstellar medium come into play? It's the gas and dust within these filaments that make up a significant portion of the cosmic web. This material is the raw fuel for star formation, and it's constantly flowing along the filaments, feeding galaxies and clusters. Without the interstellar medium, the cosmic web would be a lifeless framework. It's this interplay between the interstellar medium and the cosmic web that drives the evolution of galaxies and shapes the universe as we know it. One of the most fascinating aspects of this connection is how the interstellar medium helps us trace the cosmic web. Because the gas and dust in the interstellar medium emit and absorb light, astronomers can use telescopes to map its distribution. By studying the light from distant quasars, for example, scientists can detect the faint absorption lines created by the interstellar medium in the filaments of the cosmic web. These observations reveal not only where the gas is located, but also how it moves and interacts with other structures. But the cosmic web isn't just a static backdrop. It's a dynamic, ever-changing network. The interstellar medium within it is constantly being shaped by forces like gravity, supernova explosions, and even the magnetic fields that thread through space. These forces can compress gas into dense clouds, triggering star formation, or stretch it into thin streams, creating the delicate filaments we observe. Over billions of years, this dance of matter and energy has sculpted the universe into the complex and beautiful structure we see today. As we continue to explore the cosmic web, we're uncovering more about how the interstellar medium connects the smallest scales like the birth of stars to the largest scales of the universe. It's a reminder that everything in the cosmos is interconnected, from the tiniest dust grains to the vast filaments of the cosmic web. Next, we'll dive into some of the biggest mysteries surrounding the interstellar medium, including the nature of dark matter and the origins of cosmic rays, and how these unsolved questions continue to challenge our understanding of the universe. As we peel back the layers of the interstellar medium, we uncover mysteries that continue to baffle even the most seasoned astronomers. One of the most profound questions revolves around dark matter. While we know that dark matter makes up a significant portion of the universe's mass, its exact nature remains elusive. How does it interact with the interstellar medium? Does it influence the formation of stars and galaxies in ways we haven't yet detected? These questions linger, challenging our understanding of the cosmos. Another enigma lies in the origins of cosmic rays. These high-energy particles, which race through space at nearly the speed of light, are thought to come from sources like supernova explosions and black holes. But how exactly are they accelerated to such incredible speeds? And what role does the interstellar medium play in their journey across the galaxy? The answers could shed light on some of the most energetic processes in the universe. Then there's the puzzle of interstellar dust. While we know it's made up of tiny particles, their exact composition and how they form remain unclear. Are they remnants of ancient stars, or do they form in the cold depths of interstellar clouds? Understanding this could reveal more about the life cycle of matter in the universe and how it contributes to the birth of new stars and planets. Even the magnetic fields threading through the interstellar medium hold secrets. These invisible forces shape the movement of gas and dust, but their origins and how they evolve over time are still not fully understood. Do they arise from the motions of charged particles, or are they influenced by larger cosmic structures? Unraveling this could help us better predict how galaxies form and evolve. And let's not forget the question of how the interstellar medium interacts with the cosmic web on such vast scales. How does matter flow along these filaments, and what determines where stars and galaxies will form? These connections between the smallest and largest structures in the universe are still being explored, offering tantalizing clues about the interconnectedness of all things. As we continue to probe these mysteries, each discovery brings us closer to understanding the interstellar medium's role in the grand tapestry of the cosmos. But for now, these unanswered questions remind us that the universe is full of surprises, waiting to be uncovered. Next, we'll explore how the interstellar medium has captured the imagination of storytellers and scientists alike, bridging the gap between science and fiction. Now, let's take a step into the realm of imagination, where the interstellar medium has inspired countless stories, films, and artistic creations. The mysteries of this cosmic material have not only captivated scientists, but also fueled the creativity of storytellers, blending hard science with the boundless possibilities of fiction. In movies, the interstellar medium often serves as a backdrop for epic adventures. Think of films like Interstellar, where the vastness of space and the swirling clouds of dust and gas create a sense of awe and danger. The interstellar medium isn't just a setting, it becomes a character in its own right, shaping the journey of the protagonists as they navigate through nebulae and cosmic storms. These depictions, while sometimes dramatized, often draw from real scientific concepts, giving audiences a glimpse into the beauty and complexity of the universe. Books, too, have explored the interstellar medium in fascinating ways. Science fiction authors like Arthur C. Clarke and Isaac Asimov have woven intricate tales where the interstellar medium plays a central role. In Clarke's Rendezvous with Rama, the mysterious object traveling through space is surrounded by the interstellar medium, hinting at its origins and purpose. Asimov's Foundation series delves into the idea of galactic evolution, where the interstellar medium is a key player in the rise and fall of civilizations. These stories not only entertain, but also spark curiosity about the real science behind the fiction. Even in video games, the interstellar medium has found a place. Games like No Man's Sky and Elite Dangerous allow players to explore procedurally generated galaxies, where they can fly through nebulae, mine cosmic dust, and witness the birth of stars. These interactive experiences bring the interstellar medium to life in ways that are both educational and immersive, blending scientific accuracy with creative freedom. But it's not just about entertainment. The interstellar medium has also inspired artists and musicians. From stunning visual art depicting swirling clouds of gas and dust, to symphonies that evoke the vastness of space, the interstellar medium has become a muse for creative minds. It's a reminder that science and art are not so different, both seek to explore, understand, and express the wonders of the universe. As we reflect on these depictions, it's clear that the interstellar medium is more than just a scientific concept. It's a source of inspiration, a bridge between the known and the unknown, and a reminder of how much there is still to discover. Whether in the pages of a book, the scenes of a movie, or the pixels of a video game, the interstellar medium continues to capture our imagination, inviting us to dream of what lies beyond the stars. Next, we'll look ahead to the future of interstellar medium research, exploring the cutting-edge technologies and missions that promise to deepen our understanding of this cosmic material. As we turn our gaze toward the horizon of discovery, the future of interstellar medium research holds immense promise. Scientists and engineers are already designing groundbreaking missions and technologies that will peel back the layers of this cosmic material, revealing secrets that have remained hidden for eons. One of the most exciting developments is the next generation of space telescopes, like the James Webb Space Telescope's successors, which will peer deeper into the interstellar medium with unprecedented clarity. These advanced instruments will allow us to study the faintest traces of gas and dust, uncovering the intricate processes that shape the birth and death of stars. Another area of focus is the development of interstellar probes, designed to travel beyond our solar system and directly sample the interstellar medium. Projects like Breakthrough Starshot aim to send tiny, light-propelled spacecraft to nearby star systems, collecting data on the composition and properties of the interstellar medium along the way. These missions could provide the first direct measurements of this elusive material, offering insights that ground-based observations simply cannot match. Closer to home, advancements in radio astronomy are opening new windows into the interstellar medium. Arrays of radio telescopes, like the Square Kilometre Array, will map the distribution of hydrogen and other elements across vast stretches of the galaxy. By studying the radio waves emitted by these elements, scientists can piece together a detailed picture of how the interstellar medium evolves over time, from the formation of molecular clouds to the dispersal of supernova remnants. Artificial intelligence and machine learning are also playing a growing role in interstellar medium research. These technologies are helping astronomers sift through massive data sets, identifying patterns and anomalies that might otherwise go unnoticed. By combining AI with traditional observation methods, researchers can accelerate the pace of discovery, uncovering new phenomena and refining our understanding of the interstellar medium's role in the cosmos. Looking even further ahead, the possibility of interstellar travel itself could revolutionize our understanding of the interstellar medium. While still in its infancy, the concept of human exploration beyond our solar system raises fascinating questions about how we might interact with and study this material up close. Imagine a future where spacecraft equipped with advanced sensors navigate through the interstellar medium, collecting samples and analyzing its properties in real time. Such missions could transform our understanding of the universe, bringing us closer to answering some of its most profound mysteries. As we stand on the brink of these exciting advancements, one thing is clear: the interstellar medium is not just a passive backdrop to the cosmos. It is a dynamic, ever-changing environment that holds the key to understanding the universe's past, present, and future. With each new mission and technological breakthrough, we move closer to unraveling its secrets, reminding us that the journey of discovery is as boundless as the stars themselves. Next, we'll explore the challenges and opportunities of traveling through the interstellar medium and what it might mean for the future of human exploration. As we venture into the next frontier of space exploration, the interstellar medium presents both incredible challenges and exciting opportunities for human travel. Imagine a spacecraft journeying through the vast expanse between stars, navigating a sea of gas, dust, and cosmic rays. The first hurdle is the sheer distance. Even the closest star systems are light years away, requiring technologies far beyond our current capabilities to make such journeys feasible within a human lifetime. Propulsion systems like light sails or nuclear engines are being explored, but they must overcome the immense energy demands and the harsh conditions of space. Another challenge lies in the interstellar medium itself. While it may seem empty, it's filled with tiny particles of dust and gas that, at high speeds, could pose a serious threat to spacecraft. These particles, though small, could cause significant damage to a ship's hull or sensitive instruments. Shielding technologies will need to be developed to protect both the spacecraft and its crew from these microscopic hazards. Additionally, The presence of cosmic rays, high-energy particles that permeate the interstellar medium, could pose health risks to astronauts, requiring advanced radiation shielding and countermeasures. Yet, within these challenges lie opportunities. Traveling through the interstellar medium could provide unprecedented insights into its composition and behavior. A spacecraft equipped with advanced sensors could analyze the gas and dust it encounters, offering real-time data on the density, temperature, and chemical makeup of this cosmic material. Such missions could help us understand how the interstellar medium influences star formation, galactic evolution, and even the potential for life beyond Earth. Moreover, the journey itself could lead to technological breakthroughs. Developing propulsion systems capable of interstellar travel would revolutionize not just space exploration, but also our understanding of physics and engineering. The need to protect spacecraft from cosmic rays and micrometeoroids could drive innovations in materials science, benefiting industries far beyond space travel. Human exploration of the interstellar medium also raises profound questions about our place in the universe. What would it mean to travel through the very fabric of space, to witness firsthand the processes that shape stars and galaxies? Such missions could inspire a new era of discovery, pushing the boundaries of what we believe is possible and deepening our connection to the cosmos. As we look to the stars, the interstellar medium stands as both a barrier and a gateway. Overcoming its challenges will require ingenuity, collaboration, and a bold vision for the future. But the rewards unlocking the secrets of the universe and expanding the horizons of human exploration are worth the effort. Next, we'll connect the dots between the interstellar medium and the broader universe, exploring how this cosmic material ties into the grand tapestry of cosmic evolution. Now, let's step back and see how the interstellar medium fits into the grand scheme of the universe. This cosmic material isn't just a backdrop for stars and galaxies. It's a vital player in the story of cosmic evolution. From the birth of stars to the formation of planets, the interstellar medium is the thread that weaves together the fabric of the cosmos. At its core, the interstellar medium is the raw material from which stars are born. When massive clouds of gas and dust collapse under gravity, they ignite the process of star formation, lighting up the universe with new suns. These stars, in turn, shape their surroundings, heating and ionizing the gas around them, and even seeding the interstellar medium with heavier elements when they explode as supernova. This cycle of creation and destruction is a fundamental part of how galaxies evolve over billions of years. But the interstellar medium's role doesn't stop there. It also acts as a cosmic recycling system. When stars die, they release their material back into space, enriching the interstellar medium with elements like carbon, oxygen, and iron. These elements become the building blocks for new stars, planets, and even life itself. Without this continuous exchange of matter, the universe as we know it wouldn't exist. On a larger scale, the interstellar medium is deeply connected to the structure of the universe. It forms the backbone of the cosmic web, the vast network of gas and dark matter that spans the cosmos. This web channels the flow of matter, guiding the formation of galaxies and shaping the large-scale structure of the universe. In this way, the interstellar medium isn't just a local phenomenon, it's a universal one, influencing the evolution of the cosmos on the grandest scales. Understanding the interstellar medium also gives us a window into the past. By studying its composition and behavior, we can trace the history of the universe, from the first stars to the present day. It's like reading a cosmic history book, written in the language of gas, dust, and light. In the end, the interstellar medium is more than just the space between stars. It's the glue that holds the universe together. It connects the smallest particles to the largest structures, the past to the present, and the known to the unknown. As we continue to explore its mysteries, we're not just learning about the interstellar medium, we're uncovering the story of the universe itself. And that story is still being written, one star, one galaxy, and one discovery at a time. As we bring our journey through the interstellar medium to a close, let's take a moment to reflect on what we've uncovered. This vast expanse of gas, dust, and cosmic rays isn't just empty space. It's the lifeblood of the universe. From the birth of stars to the formation of galaxies, the interstellar medium plays a central role in shaping the cosmos as we know it. It's a cosmic recycler, a star factory, and a storyteller, holding clues to the universe's past and its future. We've seen how the interstellar medium serves as the raw material for stars, igniting the process of star formation and lighting up the darkness of space. We've explored how it's enriched by the death of stars, scattering elements like carbon and oxygen back into the void, where they become the building blocks for new worlds and even life itself. And we've discovered how it connects the smallest particles to the largest structures, weaving the cosmic web that defines the universe's grand architecture. Yet, for all we've learned, the interstellar medium remains a place of mystery. What drives the movement of interstellar winds? How do magnetic fields shape the flow of gas and dust? And what secrets do dark nebulae hold, hidden in their shadowy depths? These questions remind us that the universe is still full of wonders waiting to be uncovered. As we look to the future, the interstellar medium will continue to be a frontier of discovery. New telescopes, advanced technologies, and bold missions will deepen our understanding of this cosmic material, revealing even more about its role in the universe. And as we explore, we'll not only learn about the interstellar medium, we'll learn about ourselves, our place in the cosmos, and the incredible story of how we came to be. So, as we leave the interstellar medium behind, let's carry with us a sense of wonder and curiosity. The universe is vast, complex, and endlessly fascinating, and the interstellar medium is just one chapter in its grand story. What other secrets does the cosmos hold? What new discoveries await us in the depths of space? The answers are out there, waiting to be found, and who knows, maybe the next great discovery will be yours. If you enjoyed this journey through the mysteries of the interstellar medium, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an exploration into the wonders of the universe. Thanks for watching, and until next time, keep looking up. The cosmos is waiting. you.